So recall the identity matrix. This was written as the matrix I, which for a given dimension has 1 along the diagonals and 0 everywhere else. And this had the algebraic property that when I multiply it by any matrix in either order, I just get that original matrix back. This lets us introduce the idea of inverse matrix. Now, not every matrix has an inverse. If it does, we'll define the inverse. We'll first denote it as A to the minus 1 to be the matrix that when we multiply it by our matrix A in either order, that's not an I, it's a minus 1, these cancel to give you the identity matrix. That's the matrix inverse. So there are a few properties that we have for inverse matrices. First off is that the inverse matrix is unique. There's only one for a given matrix A. To prove this, suppose that we've got two inverses. Suppose A has inverses B and C. Suppose these matrices both have this cancellation property with A. In that case, just to write it out, that means that A times B in either order gives you identity, and A times C in either order gives you the identity. If that's the case, you can write out BAC, and by the associativity of matrix multiplication, you can group the first two together, or you can group the last two together. Now B times A is the identity because these are inverses. And on the right-hand side, A times C is the identity because they're inverses. And now the identity, when we multiply that by any matrix, just gives itself, and the same on the right-hand side. So that says we had two inverses, turns out they're actually the same matrix. So it just says that there is only one inverse for a given matrix, if there is an inverse at all. Okay, we also have the idea of double inverse. And this, if we take the inverse of the inverse, that just gives us the original matrix back. And as a proof of this, if we see that A times A inverse is the identity, provided A has an inverse in the first place. And now if we look carefully at this, A inverse inverse is the matrix that when you multiply it by A inverse, you get the identity. Well, we've already found such a matrix. It's the matrix A. And so I know that A times A inverse is identity by what we just have up here. And by definition of inverse, A inverse inverse times A inverse is the identity. So now this A and this A inverse inverse are playing the role of B and C from the previous step. So by the uniqueness of inverses, I know that they've got to be the same. A inverse inverse has to be the same as A. Okay, we've got a few more properties. These should go fairly quickly. Next up is that if we multiply a matrix by itself and take the inverse, this is the same thing as inverting each and then multiplying. And you can see this by saying, well, if I have A times A, I want to find a matrix so that when I multiply these together, we get the identity. So what we'll do is multiply both sides by A inverse. So here on the left, the A's cancel to give you the identity, which multiplies through to give you just A times X is A inverse. And then we multiply by A inverse again. So we multiply by A inverse a second time, A inverse a second time. Now the A's here cancel again. So that says that our inverse is actually A inverse, A inverse. Okay, and you can repeat this. You can see that the same idea holds if you've got a bunch of matrices multiplied together to give you inverses. This is just the inverse multiplied by itself the same number of times. Okay, we've got also the inverse of a scalar multiple. If I scale a matrix and take the inverse, this is the same thing as taking the reciprocal of the scalar and the inverse of the matrix. And to see this, if I take C times A, and I want to find its inverse, well, that's going to be the matrix. Let's just call that X for now. It's going to be the matrix so that when I multiply it by CA, I get the identity. Okay, well, to get the identity, let's multiply on the right both sides by A inverse. So that gives me X times C equals A inverse. Then I need to get rid of the C somehow, so I can multiply both sides by 1 over C to get rid of the scalar multiple, which says this is 1 over C times A inverse, which is what we're trying to show in the first place. It just says the inverse of a scalar multiple of a matrix takes the inverse of the scalar multiple and the inverse of the matrix. Okay, and then finally we've got the idea of a transpose. So if I take A transpose inverse is the same thing as A inverse transpose. So this is that we can do the transposition in either order. So to prove this, we can take A. If I look at A times A inverse, I know this is the identity. Now if we transpose both sides, I have some properties of transposes. If you recall, when you transpose a product, the things switch around. So we get A inverse transpose times A transpose equals. Now if you transpose the identity, remember transposing switches everything around the diagonal, so we just get the identity again. Okay, now this last statement we have right here says that the inverse of this matrix, the inverse of A transpose, is the one that when you multiply it by it gives you the identity. So this is the inverse of A transpose. So that tells us that A transpose, the inverse of A transpose is this matrix right here by uniqueness of inverses. So those are the basic properties we have for inverses. So after all that, let's actually do something concrete. So we got a bunch of these properties down. Let's take a look at how to actually verify you have an inverse, or how to find an inverse. Let's say that A is the matrix 1, negative 2, 3, negative 5, and B is the matrix negative 5, 2, negative 3, 1. Let's verify that these are inverses. It means we've got to take A times B. If we write this out, 1, negative 2, 3, negative 5 times negative 5, 2, negative 3, 1. Let's actually do the matrix multiplication. So remember, we're going to get the entry in the first row, first column, we dot product the first row and the first column. So that's going to give us negative 5 plus 6 is 1. To get the entry in the first row, second column, we dot product the first row with the second column. That's going to give us 2 plus negative 2 is 0. So far it's looking good. To get the entry in the second row, first column, we'll dot product the second row with the first column. So we're going to get negative 15 and positive 15 is 0. And then to get the entry in the second row, second column, we dot product the second row with the second column. It's going to give us 6 and negative 5 is 1. So that looks good, but that's only half the picture. We verified that when you multiply them in this order, they cancel. Let's do the multiplication in the other order also. So we need to take negative 5, 2, negative 3, 1, and multiply it by the matrix A. 3, negative 5. So again, to get the entry in the first row, first column, we'll dot product the first row with the first column. And that gives us negative 5 plus 6 is 1. To get the entry in the first row, second column, we dot product the first row with the second column. That's 10 and negative 10, which is 0. Then to get the entry in the second row, first column, we'll dot product the second row with the first column. We'll get negative 3 plus 3 is 0. And then finally, to get the second row, second column here, we'll dot product the second row with the second column. That gives us positive 6 and negative 5 is 1. So that verifies that A and B are inverses of one another. So that's how you can verify inverses. Let's see how you can actually find one. The idea here is to find the inverse. We're going to take the matrix A, augment it with the identity, and perform elementary row operations on this until we reduce A to the identity matrix. And then whatever matrix is over here is the inverse. Let's illustrate this with an example. We're going to need a little bit of room for this. So let's move over here. Let's say we've got the matrix A is, we'll do a 3 by 3. We'll do 1, 1, 2, 2, 4, negative 3, 3, 6, negative 5. And then we're going to augment this with the identity matrix. 1, 0, 0, 0, 1, 0, 0, 0, 1. And now we want to row reduce this. So for our first row, we already have a leading 1 in the first row, so that'll just sit there. 112, 100. Now, to get rid of the 2 in the second row, we can multiply the first row by -2 and add it to the second. So -2 plus 2 is 0. -2 plus 4 is 2. -4 plus -3 is -7. -2 plus 0 is -2. 0 plus 1 is 1. 0 plus 0 is 0. And then we can get rid of the 3 in the bottom row in the same way. We can multiply the top row by -3 and add it to the bottom row. So -3 plus 3 is 0. -3 plus 6 is 3. -6 and -5 is -11. -3 plus 1 plus 0 is -3. 0 plus 0 is 0. 0 plus 1 is 1. So far it's looking pretty good. We've cleared out everything else in the first column, so we have our leading one here. Now we need to get a leading one in the second column. However, if we divide the second row by 2, we're going to have a bunch of fractions, and I'd rather not have those. If we divide the bottom row by 3, we'll have fractions. However, we can do some, if we're a little more clever about this, what we can do is we can multiply the second row by -1 and add it to the bottom row. That'll make this a 1 without dividing. So that's a good idea. So let's go through and do that. So we're leaving the top row as is, 112, 100. We're leaving the second row as is, 0, 2, -7, -2, 1, 0. And now we're adding -1 times the second row to the third row. So 0 plus 0 is 0. -2 plus 3 is 1. 7 plus -11 is -4. 2 plus -3 is -1. -1 plus 0 is -1. And 0 plus 1 is 1. Now that we've got a 1 here, we want to get the leading one in the second row. So now we'll switch these two rows. So we'll let the top row just sit, 100. We'll switch the bottom two, so this becomes 0, 1, -4, -1, -1, 1. And then now our old row 2 will move down to the bottom row, 0, 2, -7, -2, 1, 0. Okay, now I have a 1 in this spot. That's good. Let's clear out everything in the same column as that 1. So what we'll do first is we'll multiply by -1 and add it to the top row. So our top row, well, our middle row will just sit there, 0, 1, -4, -1, -1, 1. Now we're adding -1 of these to the top row. So 0 plus 1 is 1. -1 plus 1 is 0. 4 plus 2 is 6. 1 plus 1 is 2. 1 plus 0 is 1. -1 plus 0 is -1. Now to get rid of that bottom row, we now need to clean that 2 out. So we'll multiply the second row by -2 and add it to the bottom row. So we've got 0 plus 0 is 0. -2 plus 2 is 0. 8 plus -7 is 1. Positive 2 and -2 is 0. Positive 2 plus 1 is 3. -2 plus 0 is -2. Okay, now, so we've got a leading one in the first column, a leading one in the second column. It looks like we also have a leading one in the third column. So now let's clean out everything else here. What we can do is we'll let the bottom row just sit there, 0, 0, 1, 0, 3, -2. Okay, so I can get rid of the second row if I multiply the bottom row by 4 and add it to the second. So 0 plus 0 is 0. 0 plus 1 is 1. Positive 4 plus -4 is 0. 0 plus -1 is -1. 12 plus -1 is 11. -8 plus 1 is -7. So that takes care of the second row. And now we can do the same thing. We can eliminate the top row by multiplying the bottom row by -6 and adding it to the top. So 0 plus 1 is 0. 0 plus 0, I'm sorry, 0 plus 1 is 1, not 0. Let's make that a 0, 1. 0 plus 0 is 0. -6 plus 6 is 0. 0 plus 2 is 2. -18 plus 1 is -17. 12 plus -1 is 11. So we've reduced this to the identity matrix on the left-hand side, and so this is our inverse. We know that A inverse is that 3 by 3. 2, -17, 11. -1, 11, -7. 0, 3, -2 is our inverse. So that's the process of actually finding an inverse.